Okay, section 3.1, part 3. So we're going to be looking at energy transfer and also energy transformations. So remembering all the different types of energy that we visited last week. So you really need to sort of keep in the back of your mind today. So the law of conservation of energy. We looked at the law of conservation of mass when we looked at chemistry. It said matter couldn't be created or destroyed. Okay, law of conservation of energy, same deal, except for it says that energy can neither be created nor destroyed. It's transformed from one form of energy to another, or it is transferred from one object to another. So transformed from one form of energy to another, or transferred from one object to another. So even if the amount of energy in one object changes, that energy hasn't been created out of nowhere, or it hasn't been destroyed. It's just coming from somewhere else or going somewhere else. Okay, so if we have a battery connected to a light bulb, this is going to be a sort of fairly simple circuit. It's probably something you took a look at in your electricity unit in Science 9. So really important in order to actually have a full circuit. We do need to draw in a second wire, because if we don't have two wires, we don't have a complete circuit and no energy is going anywhere. Okay, so looking at types of energy transformations and energy transfers that are actually occurring here. So it says label it and you refer to figure 3.5. We're just going to do it together. So we have a battery. So the battery on its own is going to be chemical potential energy. Okay, so if the battery is just sitting there and nothing's plugged into it, it's not really doing anything. It's just full of chemical potential energy. Okay, and then that is going to be converted into electrical potential energy. Okay, and then that is going to become electrical kinetic energy. As those charges start moving. Okay, and then it goes into our light bulb. And the point of our light bulb is obviously to give off light energy. So we have radiant energy, which is light. And then it also ends up giving off some heat. So especially if it's one of these incandescent light bulbs, so one of these sort of like older style of light bulbs, they actually do get really, really warm. Like you can't change a light bulb if it's been on for any length of time at all recently. If it's a CFL or an LED, they don't get nearly as warm, but they still give off a little bit of heat energy as well. So the goal of the battery is to create light energy, but as we just noted, not all of it actually gets converted into light energy. Okay, so we do end up with some heat energy that is created as well. So no energy transfer that can happen is ever going to be 100% efficient. So some of the energy from the battery gets transformed into an unusable byproduct. So in this case, it's either heat or thermal energy. So our law of conservation of energy, our total amount of energy before is still equal to our total amount of energy after. But the difference is that not all that energy is what we were actually trying to do. So we have our useful energy after. So in this case, this would be the light or radiant energy. Okay, and then our not so useful one would be the heat or thermal energy. So, anecdote, when people started making the switch from incandescent to like compact fluorescent and LED light bulbs, it was done because they were more energy efficient. So you were going to use less energy, your electricity bills would be lower by buying these new light bulbs. And what people found was that their energy bills really weren't going down nearly as much as they were sort of predicted that they would. And what it was that the light bulbs, the old light bulbs, have been giving off heat. And so it had actually been helping to heat people's homes. And so once they switched to LED and compact fluorescent, light bulbs were giving off less heat, which meant people actually had their furnaces running for more of the day. So maybe not the goal that they were looking for, but it's still good. Like, they still last for a lot longer. You don't need to replace them as often. It keeps a lot of stuff out of the landfills. So it's still a good move, just not exactly the goal that they had in mind. So there are different types of systems. So we talked about having a system in the surroundings and that making up the universe. So we have different types of systems that we can look at, and those kind of dictate what happens with our energy and how much of it is lost or whatever. So sometimes non-useful energy is considered to be lost. So because it's not doing what you're supposed to do, so it's not being converted into light, therefore it's energy that's being kind of just given away. Different types of systems are going to determine if in fact the energy is going to leave the system or if it's going to be transformed into something else. So if we have an open system, both energy and matter will be exchanged with its surroundings. Okay, so if we boil a pot of potatoes without a lid, both heat and water vapor will escape. Okay, so if you boil a pot of water and just leave it boiling, eventually it will boil dry because your water vapor is all kind of leaving, and obviously heat's going with it. If you've ever put your hand above a pot of boiling water, you know it's really, really hot up there as well. A closed system can exchange energy, but no matter with its surroundings. So if you put your lid on your pot of potatoes, now it'd have to be a really, really well-fitting lid to not have any water vapor or steam escaping. But if you had a really, really well-fitting lid where no water particles could get out, you'd still end up with heat escaping. You'd still be able to feel that warmth around the pot. And then if you have an isolated system, it's a system that you don't have any exchange of energy or matter with its surroundings. So if you boil a pot of pot of potatoes in a sealed insulated cooler, nothing can escape. And I don't actually know how you would manage to set this up to work, but in theory, nothing would escape. Okay, so if we look at an open system for an uncovered pot of boiling water with potatoes in it, so you're going to see my super terrible art skills right now. Okay, there's my pot. Okay, I'm not going to bother drying the potatoes, but we've got heat and water vapor escaping. Okay, so we have both energy and matter leaving the system. Okay. So water vapor is leaving, it'll condense on other things that are nearby, and then, yeah, heat as well. Okay, if we look at a pressure cooker with boiling potatoes, so this would be your very, very well-fitting lid. Same deal, we're going to have our pot. Here's the handle. Here's the lid for it. Okay, and you're still going to get a little bit of heat escaping. Okay, so heat leaves the system, and that's our energy. But water, which is the matter, stays. Okay, so we can have energy leaving the system, but no matter leaving the system. If we then take our pot of potatoes, and it really doesn't matter at this point which type of pot it is, so I'm going to draw my no lid one. There is my heat and water vapor. But instead of leaving it in the open, I'm going to put it in some kind of an insulated container. Okay, so if this was a perfect isolated system, we would have no energy or matter leaving. Okay, so all of that heat would still be trapped within that insulated container that's insulated from its surroundings. All of the water vapor, it would just condense kind of on the inside of that insulated container. Although if none of your heat's escaping, it's probably not going to cool down either. And so you just end up with a whole bunch of water vapor there until I guess it boils dry, but you would still just have water vapor filling that space. So none of the actual water particles would end up leaving. Now, it is impossible to do this in real life, having a totally isolated system in real life, because any kind of an insulated container are not going to be 100% perfect. Okay, so energy can still get in and out. Okay, so if you think about a cooler, it doesn't matter how great your cooler is, at some point all of the ice inside of it is going to melt. There's plenty of coolers out there that will keep ice as ice for 24 hours, some a little bit longer. And that's assuming that you're not constantly opening and closing it, because if you open and close it, you are no longer having an isolated system. But at some point, enough heat energy is going to get in that water is going to be formed, that the ice is going to melt. So we do not have an insulated container that has no energy transfer. So therefore, it's a really great idea, but not terribly practical. Okay. So if a system releases energy, the surroundings absorb it. Okay. And if a system absorbs energy, it's because the system released it. Okay. Sorry, that should totally say surroundings. That makes way more sense. Okay, so if a system is releasing energy, it's because the surroundings are absorbing it. And if the system is absorbing energy, so it's taking in more energy, it's because it was released from its surroundings. Okay, so you're going to make that change in your notes. The process can involve energy transfer, energy transformation, or both. So anytime energy is transferred, it means it's staying in the same form, it's just going to a different place. If energy is transformed, it means that our actual form of energy is changing. Okay, so if we think about a pool table, if one pool ball strikes another pool ball, this is what happens. We have mechanical kinetic energy from the moving ball, and then it hits another ball. So the second ball, the ball that was just hit, starts to move, which means it's getting mechanical kinetic energy. But you also hear that crack sound when it hits. So there's sound energy released. There's also a bit of heat generated in that contact from friction. So you've got thermal energy being released. Okay, so the mechanical kinetic energy is transferred to more mechanical energy in the second ball. But it's also transformed into sound and thermal energy, and that's why your second ball is never going to travel quite as fast or as far as the first one.